Good afternoon. My name is Priscilla. I am a postdoc research in the Biophotonics lab. I will invite Professor Timothy Zhu. It's a pleasure to receive you here in our school. Timothy is a professor at the Department of Radiation Oncology from University of Pennsylvania. His research has focused on physics, PDT physics, and external beam treatment planning. The first area involves the development of explicit and implicit dosimetry of PDT and light fluence rate calculation. And the second area involves development of benchmark database for external beams, electrons, photons, and protons, and image co-registration. Thank you, Professor.
Thank you so much, and thank Dr. Baganto and Christiana for organizing this meeting, for inviting me to come here, and I really enjoyed it. So what I'm going to talk about today is an old really topic on in vivo light dosimetry. And the reason I picked this topic is because it's very important for photodynamic therapy, especially for using clinic settings. So I'm going to go over some basic quantities about the quantities that's going to be measured, and talk about the scattering sphere-based isotropic detector, and the detector characteristics, including the correction factors that one has to take into account. And then I give some examples of in vivo light dosimetry and make a comparison between the measurement versus the calculations. So the first thing is the basic dosimetry quantities that is being used for light dosimetry. So these are all taken from William Starr's famous paper on light dosimetry in vivo, published in PMB. The most fundamental quantity in light dosimetry, as you probably all well known, is the sorry, I got it. It's the irradiance. So this is really the fundamental quantities for all light dosimetries. That is defined as power per unit cross sections, per unit solid angles in a given direction, and per unit area. And once one knows the irradiance, then you can calculate all the other quantities that can be derived from radiance, such as light fluence rate, which is the integral of the radiance over all angles. So this is the light fluence rate, and which really is the quantity that's mostly be measured in light dosimetry. Or irradiance, which is also commonly measured. The only difference between irradiance and light fluence rate is one has a directional component. So it really is the normal components shooting into area of interest is being counted for. And for PDT especially, one really don't worry too much about which angles the light coming in. It's the energy being absorbed. So the light fluence rate really is the most important part. And one associated quantity is the power of the light source. And one can determine that by integration of irradiance over the area. But this is basically inherited quantity that describes the light source being used in PDT treatment. So these are a summary of quantities: radiance, light fluence rate, radiance, power source, wavelength, area, and the associated unit for each quantities. So compare between light fluence rate and the irradiance. Really, the only difference is one has directional components taken into account. And so if one's shooting into an area at an angle theta, then the radiance will be a cosine theta smaller than the corresponding fluence rate, because fluence rate doesn't take into account angular dependence. So light fluence rate really is the quantity that determines the so-called PDT dose. That's the dose absorbed by the drug for photodynamic therapy. And the typical diodes, like flat photodiode, is measuring irradiance because it's has taken into account the angular dependence. If the light is shooting at the 90 degrees towards the area of interest, you get registered no dose with a photodiode directly. And the isotropic detector really is one of the detectors that accounts for the light coming into an area from all directions. So it measures the fluence rate. So when there is a parallel normal incidence, under that normal condition, the fluence rate is equal to the irradiance. This really is the low limit when they are equal. But normally, the fluence rate is always larger than the irradiance in most of cases. So if you look at it, that the most extreme case is isotropic light source shooting into an area where your fluence rate will be 4 times of irradiance if you just use the definition of the fluence rate and do a calculation. So all these are just to emphasize the difference between the irradiance and the light fluence rate, and the quantity we really want to measure is the fluence rate. And the fluence rate is the quantity that's used to define the PDT dose. That is defined as the number of photons absorbed by photosensitizers per tissue weight. So here, epsilon times C is the concentration of the drug concentration. That gives the absorption coefficient of the sensitizer, and that multiplied the fluence rate is giving you the PDT, the energy released to the drug. And one can also divide it by the H nu by converting that quantity to the number of photons absorbed by the drug, or and per unit mass of the tissue samples being of interest. So the second one I really want to concentrate on is the spheric scattering sphere-based isotropic detector. So these are the detectors that has been in existence for a long time. Compare that to a flat photodiode, which basically is a photodiode, directly buried into water resist material, so you can use that directly. And the mechanism of scattering isotropic detector is one has a sphere that is highly scattering, so the light coming in from any directions into this sphere will be scattered so many times that by the time they get into the fiber inside, that they don't know which direction light is coming from. So as a result, it's giving you ideally same response from all directions. Of course, if you look at this particular configuration, one can see there is potential for that spot if the light is coming from stern end, and that's one thing one have to correct for. That's a blind spot. And there's also the question about the isotropies, which we'll discuss later. And here is schematics. So typically isotropic detector system, which is the scattering bulb fitted with fibers, and that use a SMA connector, connecting to a photodiodes that connects through a preamplifier, A to D converters that computer can acquire the data after the signal is amplified. This is what the dosimetry system could look like. So one thing one has to do is to convert the signal, which is the voltage received by the dosimetry system, to the light fluence rate. And that can usually done through one of the 2 ways of this calibration. One is so-called the collimated beam calibration, where you shooting a collimated light into an area of the known area size, and then you measure the power of the light at these locations, which will give you the light fluence rate at that location, or irradiance. Since for collimated beam, irradiance is the same as light fluence rate, you basically can have a standard established and put the isotropic detector here from the calculated fluence rate and match with the measured value. It will give you this quantity A and B, and that will allow us to determine the light fluence rate. And A and B, really, A is basically the important proportional constant. B is the leakage, which usually is a constant. When there's no light, the signal should be 0. The other more common way of doing the calibration is using an integrating sphere. The advantage of using integrating sphere is, in that case, the light is coming in from all directions to the isotropic detector, so your calibration will really account for properly the signal is from all directions, and which is more suitable to be used inside the tissue for interstitial applications. And the only difference here is to quantify the known light fluence rate inside this integrating sphere. So one can stick in a light source that will be hit on a baffle, but then multiple scattering inside the integrating sphere. And a detector will be quantify the light fluence rate from this light source. And once the light source is known, which can be determined, at least in our place, is transferred from this collimated beam conditions to determine the isotropic integral sphere's light fluence rate. That will allow us to determine the quantity to do the calibration. So before we can use it clinically, the isotropic detector has to quantify to determine its characteristics. And so one area to characterize is the isotropy. So there's two angles so one can typically measure. One is so-called the vertical direction, that is perpendicular to the stand direction for the isotropic detector. That direction usually is easier to fulfill the isotropy because it's very symmetric in this end. The other direction, in horizontal direction, that is horizontal to the stand and the isotropic detector. In this particular direction, then depending on how the isotropic detector is made, they may not be isotropic. So I give you two examples. One is Cardi-focus isotropic detectors, 0.5 millimeter spherical ball. In the vertical directions, it's easier. You can see the isotropy. This is actually for a series of 6 different detectors. You can see they are very relatively uniform to within 30% for different detectors. But in the horizontal directions, you can see the isotropy is not guaranteed to be isotropic. So that we usually want to make it to be better than 30%. This particular one is about 60% isotropy. So it's not a very good isotropic detector, and it could introduce, in a sense, depending on where the light coming from, an error of about 60% for these detectors. And if you look at a different detector like these light detectors, that those are all commercial detectors one can purchase, you can see that the horizontal isotropy is much, much better for this particular detector, for example. Now it's within maximum of 30% and the minimum is 20%, so plus minus 30% within that range in both directions. In the vertical direction, it's an easier direction. That's a symmetric direction, so you can have a much better isotropies. So this is one first things that one has to characterize for use of isotropic detector in clinic. The second thing that is very important is most of this detector is calibrated in air, since we do that in air, in collimated beam or isotropic detector, but we use it inside a tissue. And in tissue, then one has to take into account the tissue has a different index of refraction, which we actually introduce a large correction factors called tissue correction factors, beta, that could be as large as 1.7 to 2 times the original number that has been calibrated. And so this number need to be characterized for each detector. It could be detector to detector different. And there's another issue that could be interesting, which I will discuss in quite a detail, which is you typically put your isotropic detector through a catheter interstitially into a tissue. So you introduce artificially another air layer, air hole, before you insert your isotropic detector. And the question is whether the immediate medium surrounding the isotropic detector is air now, which is the same medium as one does the calibration, and whether that is the medium that determines the detector calibration or the outermost medium that determines calibration. So we actually, this is something we, in the beginning, we have to kind of struggle with, and then we did some studies, and I show you some of these results. So the beta factor, water correction factor, is quite easy to measure. One basically make a measurement in air and in water, and water is a typical one that one can use because it's tissue-like. Index of refraction is close to the tissue, and the measurement can be done. For example, in the reference condition, you can put detector in a place where there's air, and another place there is air too. So these two measurements will give you two readings slightly different because of the divergence of the beam, inverse square law. So you can get sigma 0 at reference depths and a sigma 0 at the so-called water depths. And then one put the water there, and then you put the detector, same detector in these two different locations as well. And since the fluence rate in this plane is the same, whether you have water or not, you know, the attenuation from water, the refraction is minimum. Any difference one see, which is calculated from this ratio between the fluence rate measured in air at reference condition divided by the fluence rate measured in water at depths, divided by the other ratios, will give you this beta effect. So experimental rate is very easy to measure. Just you know, do a setup and one can measure it. And we have some measurement for a class of different isotropic detectors, depending on the size. So 1 millimeter ball tip, 0.5 millimeter. This is 0.3 millimeter, and this is SMET light ones, 0.85. And one can find that this correction factor actually is detector specific. So if you look at, we have measured quite a number of them. This one we have 26 of them. The others we have probably 10 of them. So we measure these quantities one by one, and if you can see that they are not changing too much for these different detectors. They have some changes. So one can certainly use the detector-specific correction factors, but one can also use average mean per detectors, which will give you an error of you know, less than 5%. So it's a very acceptable error for this correction factor. But if one doesn't take into account this correction factor, one can potentially introduce 100% errors in dosimetry, and that's completely due to mismatch of index of refraction between the two mediums, tissue medium and air medium. So theoretically, this is pretty well understood. Wildenstein has published a paper way back in '89 that calculated the correction factors, this beta factor, as a function of the the mediums. That this is N2 is the medium for the scattering sphere, and N1 is the outer mediums. So if you have the two median N to be different, and the calibration supposedly is done in air, which N2 is equal to 1, then you can calculate the change of the correction factor as a function of scattering sphere's index of refractions. And the magnitude is really in the same ballpark of the value we have. For example, for 0.3 millimeter isotropic detector, from this calculation you get beta equal to 1.7, which is the value that we have measured for this particular detector. And the theoretically, the reason for that can be explained here by this so-called two-medium model, where you have isotropic detector is considered to be a isotropic sphere that is only containing highly scattered medium with a mu s prime really, really high, and index refraction N2. Surrounding medium has the index refraction N1, and optic property is, you know, the absorption coefficient mu a and mu s prime is an arbitrary number. So the important thing is, if you have a known quantity of irradiance coming into the sphere, how much of this getting into this inner core, which is where the fiber is. Suppose there is R1 is the radiance for the inner core, and R2 is the radiance for the outer sphere. And the inner core, we sort of, you know, in their method, they treat it as if it's a sphere. Okay, it's so it's spherically symmetric. You can have the boundary condition really in this boundary. That's the important one that determines how much light gets into this scattering sphere. So the irradiance inside this sphere, L2, integrated over all the angles from in this direction. So when the mu is from -1 to 0, really is going, you know, backwards in this particular direction. Mu is defined as cosine theta. That quantity should equal to the L2, the radiance inside the sphere going towards the right and reflected back. And the refraction R21 really is, you know, Fresnel's refractions at these two boundaries. And mu basically is the refractive angle. Mu is the cosine theta of the refractive angles. So all these refracted light and plus the transmitted light from outside. So you have to take into account the refractance in this outer mediums, and 1 minus that is the light that's transmitted into it. So these quantity coming into the the fiber core plus the refracted fluence rate should equal to the fluence rate going in these directions. And that boundary condition will allow us to calculate very simple. It's basically a finite element model of diffusion model of these two boundaries. And the final result actually is very simple. You can determine the light fluence rate at R1 at the inside the boundary between the fiber core and the scattering sphere to be equal to proportional to incident radiance I, proportional to the ratio of the radiance, the sphere, scattering sphere radiance divided by the radiance of the core, the fiber core, and then 1 minus R21, 1, 2 divided by R21. So R12 is the scattering from median 1 to median 2, and R21 is scattering from median 2 to median 1, integrated over all the angles. So really the conclusion is very simple. It's basically saying it's independent of the optic properties in the medium. It is only dependent on the Fresnel refractions, integrated over all the angles, and that's completely determined by index of refractions of these two medium. The other thing that one has to worry about, of course, is if you put the detector halfway in, halfway out in the medians, going through the median, one actually can make a measurement, find out the correction factor. If you're completely outside of tissue in the air regions, your beta correction factor is something between 1.5 to 1.8, for example, for these three different detectors. But inside, completely inside the tissue, this no, sorry, I did it wrong. Completely inside tissue, the correction factor in water, it's 1.5 to 1.9. In the air, of course, there's no correction. But in between, you can actually find this correction factor is changing in between. So it's really not a constant. The reason for that is because the spherical ball, when it goes into the tissue, it could have half of that in the tissue, half of them outside the tissue, and which will naturally cause the a reduction of the correction factor. And that one can also take into account by including a transition period between the L and the tissue interface, depending on the size of the sphere. So beta is a function of positions, and we found that it's consistent within about 13 to 15%. Then at the interface, then the average in water, and also the correction factor is between 1.5 to 2. Okay, beta factors. The other thing that is kind of interesting is we looked into what happens if the isotropic detector is putting into a catheter with different conditions. So we can have the catheter filled with water, and we calculate this, the beta factors, and you can get some value that is, in a condition which is meeting with the theory completely, because the surrounding medium is the same medium as tissue, and you can actually, you have air-filled cavity filled with water, you get another readings. This seems to indicate that the outer water medium is very important, because the correction factor is now no longer equal to 1. Because even if the surrounding medium is air, and then you can have water-filled catheter inside air, and then you get also the surrounding medium, the correction now is equal to 1, almost 1. And then you have no catheter, put it in water. So this two condition is very close, of course. And then we looked at what happens if the detector is in different positions in catheters. So this is a summary of catheters, inside a catheter, the different positions. In air or in water-filled catheter is the same for beta, same as that for the Bell detector in water within 20%, and in a water-filled catheter in air, that is the same as the Bell catheter in air, but within 4%. The next condition we look at is if you put isotropic detector in different location. This is idealized location, right in the middle of the catheter, And one can have other conditions, for example, touching the front catheter or touching the back catheters. And that, what kind of error that we introduce. So we actually did some experiment of these different conditions for different type of isotropic detectors. And the conclusion is the variation is there, but they are varying somewhat for different conditions. But they are varying to within about 10%, okay? Whether they're touching the front wall or back wall or in between. So now we try to develop a theory to explain it. Now we have an intermediate medium. So now this condition is isotropic detector, which is N2 for the scattering medium. The core is inside with R1. And then you have a air cavity layer. And then outside there's a scattered mediums, okay? So the light is coming in from outside, and then what is the impact of this intermediate medium, which is actually non-scattering mediums on the readings of the isotropic detectors. And one actually can use the theory that's developed by William Starr earlier for two medium between the isotropic detector and outer medium. If one knows these two quantities, R12 star and R21 star, which is the irradiance inside here divided by the incident irradiance from outside. And so this is really the quantity we try to develop to determine. So if you look at how the light is coming into this catheter from outside, there's basically three different possible conditions. The initial possible condition is if the incident light is large enough, then the light has been refracted completely. There's total refraction. So these light you don't need to consider because they are totally refracted. One has to consider those light that is less than the critical angle of the incident medium and smaller than certain number, for example. Then you can have the light coming into this catheter, and then it will multiple scatter inside. And this multiple scatter really, can be scattered infinite number of times. You can, for this condition, you can calculate the light fluence getting into this particular medium into here, divide by what's inside coming in by this multiple scattering. Okay, take into account multiple scattering. So really, the additional effect is the additional interface between the catheter and the outer medium one, and additional medium between the catheter and in the medium one, and also of course, so that's two additional interface. So one actually can use this relation, and when the angle is larger than critical angle, one doesn't have to take into account. So when the angle is smaller than the critical angle, you can calculate that. So we actually can decide R12 for this particular geometry. And this can be calculated for serious conditions with, for example, outer median is air, the scattering median is 1.5 is water, and this catheter is air. And here the outer median is tissue. So when this R increases to 1, that means the total refraction start to happen. So you can see there actually three interfaces will have quite different behavior of this R12 as well as R21. And then you can calculate 1 minus R12, which is basically the Fresnel refraction integrate over all the angles, as the two-layer model has been using. And you can see actually R12, 1 minus R12 and 1 minus R21 behave quite differently as a function of index refraction of the scattering sphere, okay? And they actually change quite a bit depending on the intermediate catheter's index refractions. It can change from 1 up to 1.6 in this case, and each one corresponding to one curve. But as I mentioned before, I want to show you that formula from the two catheter models. It really is this ratio that determines the light fluence in the catheter. It's the 1 minus R12 divided by 1 minus R21. If you take that ratio, you find out, surprise, the intermediate catheter index refraction actually has no impact whatsoever. They all cancel out each other perfectly. So really, it comes down to you actually couldn't even differentiate different curves. These are different symbol, different curves. They're really hiding behind this one single curve, which is the two medium model. So we basically end up getting a series, going through this whole point, come to the same conclusion that the intermediate catheter has absolutely no impact on the dosimetry of the correction factors. And this is done for a particular outside median is 1.5, and the radiance of the catheter is twice as large as the isotropic detector. And we also did one for the radiance of the catheter is about the same, about 0.9, so they're very close. And this same series holds true. So you basically see no impact of the intermediate catheter on the correction factors for the isotropic detector. So the next correction factor is the so-called correction factors, which I mentioned before. The isotropic detector has a dead end near the stent, and if the light is coming from that dead end, the light will not be corrected. As a result of that, if one wants to use isotropic detector to measure the diffuse reflectance, for example, by putting an isotropic detector right in front of the reflectance standard, you actually will not measure the correct values. So if suppose you have 100% diffractive surface, so you're supposed to get 100% light coming back. And in reality, you get less. The reason for that is part of the reflected light didn't get into the isotropic detector. And that needs to be corrected for, because otherwise you will get the wrong result. And that quantity is called a correction factor. And it can be easily measured as well by making a measurement inside the inside air with no reflectance, and then put the reflectance there. And if you know the reflectance of the scatter median, the reading you get here is supposed to equal to 1 + 2R, 2 times the diffuse reflectance. And if it's not equal to that, the correction is due to the so-called correction factor. And we use that method to determine the correction factor for a bunch of different isotropic detectors. And as you can see, it changes quite a bit between different detectors. The 1 mm detector from Califocus is giving the smallest corrections, but it still is about 16% correction. So there's 16% light not getting into the isotropic detectors. And if you do the average, actually these two is about the same. And med light detectors, which actually is probably the only isotropic detector existing in the market, is giving one a correction about 40% of correction. So one has to take that into account, even in the in-air measurement. William Starr actually have looked deeper into what is the influence of the optic property of the scattering medians to the measured quantity. So what they determined here from this paper, PMB, in 2002, is the ratio between the measured light fluence to the real light fluence, that you know. And if you plot it out, this is the measured quantities versus the linear fit to the measured data. You can see that different type of isotropic detector, this is 2 types they use. And I think the one that's the linear nylon ones, it's close to the med light ones, okay? And you can see a correction of up to 4% corrections, depending on the albedos of the transport medium, turbine medium. Certainly, this graph is showing it's isotropic dependent, detector dependent. And if you do these corrections, you actually take a ratio of albedo of the scattering bulb, that the detector, to the tissue. You find that they actually can find a universal curve. So this is actually more useful in terms of getting a universal correction for any isotropic detector, given that you know the albedo of the scattering bulb, which people don't usually do. So and end up probably, you get something like this. It's just basically give you a correction of about up to 4% using isotropic detector. So now we know the major correction needed for the isotropic detector. Then we talk about the light fluence measurements. So one common one that one use is actually use isotropic detector, for example, for skin treatment. So you advocate people to use isotropic detector to account for the backscattering. And certainly one can also use a flat detectors which will only measure irradiance. So the question in this comparison is looking at the ratio between the light fluence rate to the irradiance, how they change as a function of tissue optic properties. And we did this quite a while back for this chest wall treatment. And you can see that we put the detector in different locations. And so the optic property below is a little different depending on locations. And these are the summary of the result, which is showing that, as I mentioned before, the light fluence rate is always higher than the irradiance, so by a factor of about 1.6. Okay, and also it is patient to patient dependent. The reason for that is the optic property for the patient is different. One can develop a theory which is basically using the scattering coefficient mu s prime and the effective mu effective. So these two quantities, the pair of mu effective and mu s prime, is giving you the entire mu a mu s prime of the optic property. You can find that they can nicely be modeled using diffusion model, the curve of what this ratio should be. I call this fluence rate divided by fluence rate in air. And the reason I use that fluence rate in air is because the denominator is basically what you calculate. If you use a given area divided by the power coming in, that's the fluence rate in area. And this curve is showing that this actual fluence rate on tissue surface is tissue optic property dependent, and it changes a lot depending on the tissue optic properties. And the dots here is the measured quantity, so you can see actual measurement and the calculation after this correction is applied. Is very, very good, very reasonable agreement. One can also look at, in this case, we actually do intraperiod studies where we actually suture the detectors in various positions. In the early phase 1 studies, we're using flat detectors, and then we convert to isotropic detector because we know better now. And the question is, because the phase 1 study, actually, it's a phase 2. Phase 2 studies, the dose limit is already established based on the flat detector and how we convert it. So we did a study about a comparison of isotropic detector versus the flat detectors. And this is basically the dosimetry system measurement. We put in 7 detectors, and you can see the 7 detectors going up to about 30. That's the flat detector dose rate. If you look at the fluence rate, they're going wide all over the place. But the cumulative fluence is actually, it's pretty reasonable. So here is the ratio between all these studies. We have about 15 patients studied. And then you can see this ratio is buried in between 2 lines. This is the ratio between isotropic detector reading versus the flat detector reading. And the bottom line is 1:1, which is when the light fluence rate equal to the irradiance. The top line is 1:5, so we're not exceeding this 1:5 limit. And we actually get an average of a 1.73, and that's the conversion we use in the end. So the summary from this study is isotropic detector reading is always larger than the flat detector readings on the tissue surface, and that ratio is dependent on the tissue optic properties, absorption and scattering properties. And the other thing one can measure is to make a measurement in a semi-infinite medians. So this is a measurement of light coming in with different radiance from very small to, no, actually this is a broad beam light coming in. And you can look at basically the distribution of light based on the Monte Carlo simulation, and then the measurement based on the isotropic detector measurement. These different curves actually is for different size of the beam, so they're going smaller and smaller and going up. And you can also look at the laterally as a function of beam size, as a function of different depths inside the tissue. In this particular case, 2 measurements are made. One is the light is shooting into the semi-infinite tissue phantom perpendicularly. The other is light shooting into it at the 45-degree angle, shooting at an angle. One thing is interesting to see is inside the tissue, there isn't too much difference inside the tissue at, at 0.5 cm below surface, 0.5, 1, and 1.5 cm below surface. Above the tissue, you see some difference here. Actually, the difference actually is the biggest above the tissue and the surface regions between the two conditions, but below the conditions, they are slightly different, and the difference predicted by Monte Carlo simulation sort of agree with the measurement using the isotropic detectors. So here come down to the summary. We have talked about the working principle and calibration of scattering sphere-based isotropic detectors. And the correction factor is necessary to account for the various conditions, angular dependence, deficient correction efficiency, and the mismatch of index refraction. And some sample in vivo light dosimetry provided for interstitial as well as superficial cases that show that they can agree with the theoretic calculations. All right, that is the end. Here is acknowledgement of our group. Andrea is a physicist. Gerald Finley is a faculty here. Anna Sharikov, Baochan Liu is postdocs. Julia and Michelle is graduate students. And also our physicians, Keith Singo is the director of PDT program, and Charles Simon, Steve Hong, Eli Gladstein, and acknowledge the grant support. Thank you very much.
Thank you, Professor. Any questions?
In doing in vivo dosimetry, of course, we don't know very well the optical properties of the tissue.
Yes.
So I understand well what you have done, but if we want to use the same thing to get the properties and to infer about the light distribution and then do the dosimetry, do you have any good idea to do that?
Yeah,
or?
that will be my third lecture. So my third lecture will be totally, completely concentrating on how do you determine the tissue optic property. So right here, I am saying you use isotropic detector to quantify the light for monitoring during the treatment. So you don't really have to worry about optic properties because you get the true light fluence rate in wherever point you put the detector there. And in order to do calculation, you are absolutely right. You have to know the optic property, and if it's heterogeneous, you have to describe the heterogeneity. So we will try to determine that in the third lecture about determination of optic properties using isotropic detector or other methods.
Anyone?
Then I have a second question. Concerning imperfections or fluctuations on, like in your case, which you did in the lab in a very well-defined geometry, how important is the real defined interfaces and things like this? In other words, how can I use some of the perfect geometry for local micro imperfection? Is that an issue, or we should not worry about?
When we initially used isotropic detector, we based solely on the assumption that surrounding median, immediate surrounding median is the most important, because it's the index refraction between these two median that determines the transmission of light into the isotropic detector. And we actually get to spin because our phantom study doesn't agree with our measurement. And that's why we did this study. Now, certainly you're right, we are using a very idealized geometry, but I think the fundamental experimental data is suggesting that it's the outmost surrounding median that determines your correction factor. And that correction factor, if you, even though it's a very big correction factor, up to, 100% correction, but once you apply it, it's actually is pretty, consistent. It doesn't change too much. So we have looked at, for example, touching the front, touching the back, or imperfections. We see about 10% variations because of that. Certainly, there is some uncertainties in that. But it's compared to the, what we want to measure, it's in the ballpark of uncertainties.
So, Tim, you concentrated in this talk on the issue of the accuracy in the use of detectors.
Yes.
But following on from Ron Allison's comments this morning, the second issue is whether or not in the clinic detectors are used at all. And so you have a lot of experience in this. Could you give us some indication of the error in the actual treatment delivery if you use a detector with or without the correction versus not using a detector?
That's a very, very good question. So the first question, I can certainly expand it to, I mean, so the first question is, one certainly, as we are advocating, want to use isotropic detector to measure the light fluence rate, because that is the quantity that determines the PDT efficacy, not to measure the irradiance. So that's the number one. And irradiance probably is the quantity which could be tissue optic property independent, depending on how you place it. So for superficial placement, you will not get any tissue diffuse reflectance. Once one has to take that into account. So our clinic's acceptable uncertainty is, believe it or not, about 15%. This is written in our protocol. So we want to actually guarantee our calibration to be within 15% accurate. And even though it's 15%, it's very hard to achieve. And the one question is whether this detector calibration factor itself over the long term, how well you can maintain it. And we have tracked it for 10 years data. We actually find that if one is not very careful, you can have the correction factor exceeding 15%. Could be up to 20% for selective detector. Majority of these correction factor in the data we collected over the time is within 8%, over 8 years. I mean, won't have to worry. You have isotropic detector you commission in the beginning, then you sterilize it, use inpatient, take it out, clean it, with all kinds of things you do with it, and how is that behave over the long term? And our data seems to suggest that it doesn't deteriorate that much over the times. And the question about, it's the same question whether is asking me, how do you guarantee, what is the uncertainty? That really is a very complicated question. Even with the data we have, our current assumption is we believe our current calibration to give you the correct calibration of the isotropic detectors. So we always do the calibration right before it's used. So we always believe that calibration to be truly correct. And even so, we are seeing about more than 15% variations using this collimated light calibration method. We have now changed to a different method using LED light source. And we see the error actually reduced with the new method. And that actually seems to be a better method. Use LED and know the light fluence inside and just use that to do calibration.
Yeah, but maybe just for the sake of the students here, I mean, Ron told us this morning when he went through the different clinical scenarios that in bladder cancer, for instance, PDT was approved. In 1993, it was approved in Canada. And the tumor results were excellent, but the treatment was never actually used in the clinic, and so patients did not benefit because there was too much damage to the normal wall. And Willem Starr showed, by using isotropic probes in the bladder, that there was a variation from patient to patient of a factor of 7. So for the same amount of light delivered, some patients got 7 times as much effective PDT dose as others. And so when that was known at the time the clinical trial was done, but the company refused to use dosimetry because they thought it was too complicated. And so because of that, the treatment was actually never used in patients, even though it was approved.
Yeah, I completely agree with you. I think that's a very good point you're making. And I know we actually doing this treatment in a more complex geometry like in pleural PDT. I believe if we do not do dosimetry for these cases, they will have a humongous, very toxic side effect. So really, it cannot even be going on without that for multiple sites. And here, this one I show one. Here I have some. Let me see. So this one you're seeing a change of light fluence rate change here is about 2.2%. Okay, from 1 to the different conditions, and in bladder it's even bigger because of integrin sphere effect, because the light is scattered around. So you can, you're getting 7 times. And inside the tissue, if you look at it, you can easily get 6 times more light if that's not taken into account. So the light inside the tissue, if one does not take into account correctly for interstitial application, you will get even larger error because of such a strong dependence on tissue optic properties. So the change inside the tissue surface is much smaller than what's happening inside the tissue.
Can this probe ever be used? Does it has the sensibility to be used to different measurements that are not related to dosimetry, such as bioluminescence signal or PP9 fluorescence signal?
Yes, we used it for that. So we actually, I will show you, we have a lecture, and the next lecture I'm giving, we use the isotropic detector to get fluorescence signal, as well as using that to get the absorption spectrums. And this quantity, because it's light fluence, so we actually get much better well-defined than if you use a flat cut fiber. Then you have a kind of angle, unknown angles of light getting collected. And here you get light from all directions. So you can calculate and use it for that, absolutely. So we have used it, to collect fluorescence as well as absorption spectrums.
Okay.
Yeah.
How sensitive is this detector to the temperature because of that high scattering?
No temperature dependence. We haven't noticed any temperature dependence. For PDT, I have to take it back. We haven't used this detector for thermal type of treatment, so we don't know if you heat it up to 40 degrees higher, what will be the effect. At least for PDT, because there's no temperature, too much temperature change. In our normal range, we used it in a body where we, putting, hot water to about 20 degrees. We don't see any dependence, for that, because it's completely, dependent on index refraction. And index refraction itself is not that temperature dependent, so it, end up, you have to be really, really heated up to, 70 degrees. Then you can cause coagulations. Then you can maybe, see some change. Yeah, but then its tissue is blackened. You can see it. Yeah.
Thanks, Professor.